We need to understand both in the lunar space and the space between the Earth and the Moon. What are they doing? Why are they doing it? Does it pose a potential threat to our interests?
In the summer of 2024, a Chinese capsule touched down in Inner Mongolia, carrying the first ever samples from the Moon's hidden face.
China has long been shooting for the Moon, and these tiny lunar rocks it brought back are one of the reasons why.
What it held inside, a volcanic timeline that shouldn't exist, minerals that defy geology, and something even stranger, would ignite a quiet revolution.
These grains of lunar soil provide a glimpse into the valuable resources China wants to extract to use on Earth one day.
Because the Moon didn't just surprise scientists, it unsettled them. A moon we thought we knew. For most of human history, the Moon was a constant companion, visible, distant, and seemingly changeless. When Apollo astronauts brought back samples in the 1960s and 70s, those gray rocks reinforced a simple idea. The Moon was ancient, cold, and dead. Its volcanic heart had cooled over 3 billion years ago. Its geological clock stopped. Scientists believed there was nothing left to discover, just a static, battered world, locked in orbit and frozen in time. What we knew came almost entirely from one side, the familiar face that always looked toward Earth. The far side, hidden from view, remained mysterious. With no line of sight for communication and no missions able to land safely, it was a blank page in the Moon's story. This asymmetry in exploration created assumptions that hardened into models. Researchers filled in gaps based on data from the near side, believing the rest must be similar. It was an understandable conclusion, and a deeply flawed one. Because as China prepared to explore the far side, it wasn't just chasing lunar novelty, it was preparing to lift the curtain on everything we thought we understood about the Moon's past. China's unprecedented missions. In January 2019, China became the first nation in history to land on the far side of the Moon. The mission was Chang'e 4, and it faced a problem no other lunar lander had: silence. From the far side, Earth is invisible, and with it, all direct communication. So, China launched a relay satellite called Queqiao, placing it precisely at the Earth-Moon Lagrange point 2, a gravitational sweet spot that allowed real-time contact with the hidden hemisphere. Chang'e 4's success unlocked a new chapter in lunar science. Its rover, Yutu-2, began transmitting images and data unlike anything seen before. Scattered across the gray dust were unnaturally smooth glass spherules, formed by intense heat. More puzzling was a greenish gel-like substance found nestled in a small crater. Initially labeled as impact melt breccia, rock fused by ancient meteor strikes, the substance appeared too young, too pristine. It hinted at recent activity on a world presumed geologically lifeless. Then came the mission that would transform speculation into confrontation: Chang'e 6. In 2024, it descended into the South Pole Aitken Basin, one of the oldest and deepest impact zones in the solar system. Using a robotic arm and drill, it retrieved nearly 2 kilograms of lunar material, the first physical samples ever returned from the Moon's far side. What scientists found inside those samples challenged decades of assumptions. Volcanic rocks, dated to just 2.8 billion years ago, contradicted everything Apollo had taught. According to all prior models, lunar volcanism had ceased by then, and yet, the data told a different story. The Moon's far side was not just different in terrain, it held secrets that rewrote the rules of planetary science. Volcanism without heat. In November 2024, the samples from Chang'e 6 underwent rigorous analysis at China's Institute of Geology and Geophysics. What emerged from that examination stunned the global scientific community. Of the 108 basalt fragments studied, 107 were dated to around 2.8 billion years ago, a finding that directly contradicted the prevailing view that lunar volcanism had ended 500 million years earlier. But the shock didn't end there. These volcanic rocks were formed without the key ingredients traditionally believed necessary for sustained internal heat. Unlike samples from the Moon's near side, which contain radioactive elements like potassium, rare earth elements, and phosphorus, collectively known as creep. The far side samples were nearly devoid of them. Without these isotopes to produce heat through radioactive decay, scientists had long assumed the moon's far side couldn't have supported volcanic activity for billions of years. And yet, it did. This raised a deeper, more unsettling question. If the moon could remain geologically active without the expected heat sources, what else do we not understand about planetary evolution? Some researchers suggested tidal heating or localized mantle anomalies. Others proposed still unknown processes beneath the crust. The mineral makeup of the samples added further complexity. Unusual crystalline structures, low calcium pyroxenes, atypical olivine, and mixed regolith pointed to a geological history shaped not only by internal activity, but by far-reaching impact events. It was as if the far side had recorded collisions from across lunar history, preserving foreign material like a cosmic archive. Every new layer of evidence destabilized the old models. If volcanic activity could persist against all odds, it meant Earth's satellite, once thought to be inert, was hiding a thermal history more dynamic and mysterious than anyone had imagined. The granite that shouldn't exist. 2 years before Chang'e 6 returned its samples, NASA's Lunar Reconnaissance Orbiter had quietly detected something equally baffling. Using thermal infrared sensors, it identified a region on the far side of the moon, the Compton-Belkovich volcanic complex, radiating residual heat. This was strange in itself, but stranger still was what the data revealed beneath the surface. A massive granite formation spanning more than 50 kilometers in width. Granite is a rock we associate with Earth, specifically with continents and long-lived volcanic systems. It forms through the slow cooling of magma, often in the presence of water. The moon, with its bone-dry interior and presumed lack of tectonic complexity, wasn't supposed to have the right conditions for granite to exist. And yet, there it was. What this meant, according to planetary geologists, was that somewhere in the moon's deep past, there had been a localized, enduring heat source, something powerful enough to drive the kind of magmatic evolution seen in Earth's most ancient mountain ranges. It suggested not only volcanic longevity, but a degree of geochemical richness no one had expected from the lunar crust. This granite was not a surface feature. It was hidden, buried under ancient lava flows and impact debris, and yet still thermally distinct, as if holding on to the memory of its fiery origin. It raised an even bolder question. Had parts of the moon, in isolated pockets, evolved along a path far more Earth-like than we ever dared to consider? Helium-3 and lunar resources. While ancient granite and unexpected volcanism were rewriting the moon's geological story, another discovery was capturing the attention of governments and energy strategists alike. Embedded in the lunar regolith, especially on the far side, is helium-3, an isotope nearly non-existent on Earth, yet theoretically ideal for nuclear fusion. Unlike conventional fusion fuels, helium-3 produces little to no neutron radiation, making it an exceptionally clean energy source. Just 1 ton of helium-3 could generate enough electricity to power a major city for a year. And the moon, according to estimates based on Chang'e 5 and earlier missions, may hold over 1 million tons of it. In 2020, China announced the discovery of a new lunar mineral, Chang'e-Y, which confirmed measurable amounts of helium-3 in the regolith. The implication was immediate. This wasn't just about science. It was about energy independence on a planetary scale. Whoever could extract and control helium-3 would gain a strategic edge not seen since the dawn of the petroleum age. To that end, China has laid out a roadmap. A permanent international lunar research station is planned near the moon's south pole by 2035. The upcoming Chang'e 7 and 8 missions are designed to search for water ice, test technologies to convert lunar soil into usable materials, and establish the groundwork for sustained human activity. In this new space race, national prestige is no longer the only prize. The moon now represents something deeper, the future of civilization's energy, industry, and power balance, written not in oil, but in dust and isotope. The moon as strategic frontier. For centuries, the moon inspired poetry, myth, and quiet contemplation. Today, it's become a geopolitical chessboard. With every mission, China is executing a deliberate strategy, not just to explore, but to establish presence, build infrastructure, and stake claim to the resources of a world once considered barren. The United States, through its Artemis program, has ambitious plans to return astronauts to the lunar surface. But budget delays and shifting timelines have slowed progress. Meanwhile, China advances methodically, each robotic lander a rehearsal for permanence. This isn't just about planting flags. It's about energy futures, scientific leadership, and the rules of engagement in a domain with no precedent. As granite formations glow faintly beneath ancient lava and helium-3 shimmers invisibly in the dust, the moon is no longer the end of exploration. It is the beginning of a new frontier, one where geology, politics, and possibility now collide. The moon, once silent and still, is speaking again, through rocks, heat, and buried light. If this glimpse into its secrets sparked your curiosity, subscribe for deeper journeys, share your thoughts below, and stay with us as we explore what lies beyond Earth's final horizon.